Let's explore how we measure angles in a circle, one of the most fundamental concepts in geometry. First, we need a reference point. We'll place a dot at the center of our circle, which will serve as the vertex for all the angles we'll measure. Now we'll draw a radius line from the center to the edge. This line will act as our starting position, the 0 degrees mark, from which we'll measure all our angles. As we rotate this radius line around the circle, we'll track the angle it forms. We'll measure at 30-degree intervals, observing how the angle grows as we move counterclockwise around the circle. Notice how we've now made a complete rotation, returning to our starting point. This complete journey around the circle measures exactly 360 degrees. This is a key property of circles. A full rotation always equals 360 degrees, no matter the size of the circle. Let's reset our view to focus on another important property of circle angles. We can divide our circle into equal sections. Here, I'm dividing it into 8 equal parts. These divisions are created by drawing radius lines at regular intervals around the circle. Since we've divided the circle into 8 equal parts, each section represents 45 degrees. Notice how 8 times 45 equals 360. That's because these 8 sections together make up the entire circle. We could divide the circle into any number of equal parts, and the sum of their angles would always be 360 degrees. But this raises an interesting question. Of all possible numbers, why do we use 360 to measure a complete circle? Why not 100 or 1,000 or any other number? The answer lies in ancient history. The Babylonians, who lived over 4,000 years ago, used a base 60 number system. This system made 360 a convenient choice because it has many divisors. It can be divided evenly by 2, 3, 4, 5, 6, 8, 9, 12, and many more numbers, making calculations with fractions of a circle much simpler. The Babylonian number system, developed over 4,000 years ago in ancient Mesopotamia, holds the key to understanding why circles have 360 degrees. The Babylonians recorded their mathematics on clay tablets using wedge-shaped marks called cuneiform. Their mathematical insights were remarkably advanced for their time. While we use a base 10 system, counting by tens, the Babylonians used a base 60 system called sexagesimal. This means they grouped numbers in 60s rather than tens. In our decimal system, we have ones, tens, hundreds, and thousands. In the Babylonian system, they had ones, 60s, 3,600s, and so on. Each place value was 60 times greater than the previous one. This base 60 system wasn't just a mathematical curiosity. It shaped how we measure many things in our modern world, including angles, time, and geographic coordinates. Let's visualize how the base 60 system works. On this number line, each complete group of 60 units represents one whole unit in the Babylonian system. The Babylonians chose 60 as their fundamental unit for a practical reason. The number 60 has many divisors: 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. This made fractions and divisions much easier to work with. This mathematical convenience is why we still divide our hours into 60 minutes and our minutes into 60 seconds. These divisions are direct inheritances from the Babylonian sexagesimal system. This highlighted section represents one complete Babylonian unit of 60. Just like we think of 100 as a nice round number in our decimal system, they viewed 60 as a convenient and complete unit. Now let's see how the Babylonian system influenced our circle measurements. The Babylonians first divided a circle into 6 equal parts. Why 6? Because this division creates sectors where each side is exactly the same length as the radius. Then came the crucial step that would shape mathematics forever. The Babylonians applied their base 60 system to these 6 sectors by assigning 60 units to each sector. Let's look at how this works. Each of these 6 colored sectors gets assigned 60 degrees. When we count all the degrees around the circle, we get 6 times 60, which equals 360 degrees. This multiplication, 6 times 60, gives us exactly 360 degrees in a full circle. This wasn't arbitrary. It came directly from combining geometry with the Babylonian counting system. This 360-degree system has proven remarkably durable. It has survived for over 4 millennia and is still how we measure angles today. Having 360 degrees is incredibly convenient because it can be divided evenly by so many numbers. We can split a circle into 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 18, 20, 24, 36, 40, 45, 60, 72, 90, 20, or 180 equal parts, all giving us whole numbers of degrees. So when you measure angles in geometry class, or when pilots navigate across the globe, you're using a mathematical concept that originated with the ancient Babylonians. Their clever base 60 system, multiplied by 6 sectors of a circle, gave us the 360-degree measurement we still use today. Let's explore the fascinating connection between Earth's orbit around the Sun and why we divide a circle into 360 degrees. At the center of our solar system is the Sun, a massive ball of hot gas that provides light and heat to all the planets. Earth travels around the Sun in a nearly circular orbit path, which we call its annual orbit. Here, we see Earth with its moon. As Earth orbits the Sun, the Moon travels with it while also rotating around Earth in its own smaller orbit. One of the most important numbers to understand about Earth's orbit is that it takes approximately 365 days for Earth to make one complete trip around the Sun. This is what we call a year. If we divide Earth's circular path by 365 days, we find that Earth moves about 1 degree along its orbit each day. This small but steady movement is what ancient astronomers noticed when observing the night sky. Let's watch as Earth moves through about 30 degrees of its orbit, which is roughly equivalent to 1 month of time. Notice how the position of Earth changes relative to the Sun. What's fascinating is that from Earth's perspective, it doesn't feel like we're moving. Instead, ancient astronomers observed the Sun appearing to move against the background of distant stars. They noticed that the Sun returned to the same position in the sky after about 365 days. These early astronomers in Mesopotamia and other ancient civilizations needed a way to measure and track this circular path of the Sun through the sky. They chose to divide the circle into 360 parts, or what we now call degrees. Here we see a circle divided into 360 degrees, with markings every 30 degrees. This 360-degree circle represents the complete path that the Sun appears to make through the sky during a year. The fact that a 360-degree circle is so close to the 365-day year is more than just a coincidence. The Babylonians, who used a base 60 number system, found that 360 was a convenient number because it can be divided evenly by many different numbers like 2, 3, 4, 5, 6, 8, 9, 10, 12, and more. This made calculations much easier for them. With this system, each degree of the circle corresponds almost perfectly to 1 day of Earth's orbit. As Earth moves through its yearly journey, it travels approximately 1 degree per day. Ancient astronomers could use this to track seasons and predict important events like planting times and religious festivals. This beautiful connection between Earth's natural cycle and our mathematical system for measuring angles has remained with us for thousands of years. Even today, when we measure angles in degrees, we're using a system that was inspired by Earth's journey around the Sun. Let's explore how we measure angles in a circle, comparing degrees and radians, 2 different but equally valid ways to measure angles. This is a unit circle with radius 1. A unit circle is special because its radius is exactly 1 unit, which makes it perfect for understanding angle measurements. I'll rotate this yellow line around the center of the circle. As I do, we'll track the angle in both degrees and radians to see the relationship between these 2 measurement systems. Watch carefully as we rotate the line around the circle. You'll notice that degrees increase from 0 to 360, which you're probably familiar with. At the same time, radians increase from 0 to 2 pi, which is approximately 6.28. As you've just seen, a complete circle can be measured as either 360 degrees or 2 pi radians. This means that 180 degrees equals pi radians and 90 degrees equals pi over 2 radians. These two systems are just different ways to express the same angles. To better understand radians, let's visualize what happens when we unwrap a circle into a straight line, almost like unrolling a wheel along the ground. Remember that the circumference of a circle equals 2 pi times its radius. For our unit circle with radius 1, the circumference is simply 2 pi, or about 6.28 units. This is how far you'd travel if you walked around the entire circle once. When we unwrap our circle into a straight line, that line has the same length as the circle's circumference, exactly 2 pi units. This straight line represents all the points that were originally on the circle's edge. Now let's explore what exactly 1 radian means. It's a key concept that makes radians so useful in mathematics. 1 radian is defined as the angle formed at the center of a circle when the arc length equals exactly 1 radius. Think of it this way. If you walked along the circle for a distance equal to the radius, you would have traveled 1 radian of angle from your starting point. Since we can fit exactly 2 pi radius lengths around the circle's circumference, there are exactly 2 pi radians in a full circle. This gives us the conversion formula. 360 degrees equals 2 pi radians, or approximately 6.28 radians. Now that we understand what degrees and radians are, let's compare when and why we might choose one over the other in real-world applications. Degrees are familiar and intuitive for everyday use. We're used to thinking about right angles as 90 degrees, straight lines as 180 degrees, and full circles as 360 degrees. This system makes sense to us because we can easily divide a circle into equal parts, like quarters, thirds, or sixths. Degrees are widely used in navigation, engineering, and construction because they're convenient for communicating and measuring angles in the physical world. A compass, for example, is divided into 360 degrees to help us find our way. Radians, however, are the preferred choice in mathematics, especially in calculus and advanced physics. The reason is that radians create more elegant formulas without the need for extra conversion factors. When working with trigonometric functions in calculus, radians make formulas simpler. For example, the derivative of sine x equals cosine x, but only when x is in radians. If we use degrees, we'd need an extra conversion factor, making the formula more complicated. This mathematical elegance is why scientists, engineers, and mathematicians use radians for advanced work. When you move beyond basic geometry to calculus and physics, radians make the math flow more naturally because they directly connect the angle measurement to the circle's radius. Both systems have their place. Degrees provide a practical 0 to 360 scale for everyday measurements, while radians offer a natural connection to the circle's radius, making them perfect for mathematical analysis. Understanding both systems and how to convert between them gives you the flexibility to use the right tool for each situation. Let's explore real-world applications of the 360-degree system, starting with navigation. Throughout history, humans have needed ways to find their direction accurately. A compass divides a complete circle into 360 degrees, giving us the ability to navigate precisely in any direction. The 4 cardinal directions, north, east, south, and west, serve as our primary reference points. Beyond these 4 main directions, the compass is further divided into smaller increments. Typically, we see markings every 30 degrees, allowing for more detailed navigation. Each marking represents a specific bearing or heading that sailors, hikers, and pilots can follow. The compass needle is the heart of this navigation tool. As it rotates, it can point to any of the 360 degrees in a circle. For example, if you need to travel northeast, you would follow a bearing of 45 degrees. If you need to go southwest, that's 225 degrees. This precise system allows us to navigate even when there are no landmarks or when visibility is poor. Another important circular measuring tool is the protractor, which architects, engineers, and students use regularly to measure and create precise angles. Unlike a compass, a standard protractor is a semicircle that measures up to 180 degrees. Notice how it's marked in 10-degree increments, with larger markings at significant angles like 0, 30, 60, 90, 150, and 180 degrees. This design makes it easy to measure or draw any angle for geometric problems, architectural plans, or engineering designs. Let's see how a protractor works in practice. To measure an angle, we place the center of the protractor at the vertex of the angle. One ray of the angle is aligned with the 0-degree line. Then we read where the other ray intersects the protractor's scale. In this example, we're measuring a 45-degree angle, which is exactly half of a right angle. Perhaps the most familiar circular measurement system in our daily lives is the clock. We interact with it constantly, often without thinking about its mathematical foundation. The standard analog clock face divides a complete circle into 12 hours. This means each hour mark represents 30 degrees of rotation, since 360 degrees divided by 12 equals 30. This system has been used for centuries and elegantly combines our measurement of time with the natural circular motion of the Earth's rotation. The hands of a clock demonstrate circular motion in action. The hour hand, shown here in blue, makes a complete 360-degree rotation in 12 hours, moving at a rate of 30 degrees per hour. The minute hand, shown in green, moves much faster, completing a full 360-degree rotation in just 60 minutes. That's 6 degrees every minute. This difference in speed creates the familiar rhythm of our daily timekeeping. Now that we've explored these applications, let's summarize how the 360-degree system helps us in our daily lives. These applications show us how the 360-degree circular measurement system has become essential in our lives. From finding our way with a compass, to designing buildings with precise angles, to tracking the hours of our day, this ancient mathematical concept continues to be remarkably practical. The next time you check your watch or use a map, remember you're experiencing the 360-degree circle in action.